20,000 light-years away, a star is dying. Its body stretches over 2,000 times wider than ours. If you placed it at the center of our system, its edge would reach past Saturn. Every rocky planet, every gas giant between here and there, gone, swallowed. Over the next 2 hours, we will travel from familiar giants to something that should not exist. A star so large, it breaks what physics says is possible. If you enjoy this journey, like and subscribe. Now, hold on, we are going in. Let us start with what we know. Our star sits at the center of our solar system. It holds everything together: 8 planets, dozens of moons, billions of chunks of rock and ice, all of it locked in orbit by the gravitational pull of one glowing sphere of hot gas. We wake up every morning because of it. Every green thing on Earth grows because of it. Without it, we would be a frozen rock drifting in the dark. So how big is it? If you could line up Earth side by side across our star's face, you would need about 109 of them to reach from one edge to the other. Its diameter stretches roughly 864,000 miles. That is wide enough to fit every planet in our solar system inside it, with room to spare. And it weighs about 330,000 times more than Earth. Roughly 99% of all the mass in our entire solar system belongs to our star alone. That is enormous. By any human standard, it is beyond imagination. But here is the thing that most people never hear. Our star is average, completely ordinary. Among the hundreds of billions of stars in the Milky Way, ours falls right in the middle. It is a yellow dwarf, a classification that astronomers use for medium-sized, medium-temperature stars in the prime of their lives. There are stars far smaller. Red dwarfs, for example, can be just 1/10 the width of ours. And there are stars so much larger that our star would look like a grain of sand sitting next to a beach ball. That is the journey we are about to take. And the scale of what we are going to find will be hard to accept. Because the universe does something strange with stars. It builds some of them to sizes that seem impossible. Stars so wide that light itself, the fastest thing in existence, needs hours to travel around them just once. Stars so bloated that their outer layers are thinner than the air you are breathing right now, yet they stretch across distances larger than the gap between our star and Saturn. We are going to visit them, one by one, smallest to largest, and by the end, you will understand why the biggest star ever discovered has left scientists questioning whether our models of physics are even complete. But to get there, we need to understand something first. Why do stars come in such wildly different sizes? What decides whether a star stays small and quiet for billions of years, or grows into something monstrous that burns through its fuel in just a few million? The answer starts at birth. Every star begins the same way. A cloud of gas and dust floating in space, sometimes stretching across dozens of light years, collapses under its own gravity. The center heats up. Atoms slam together faster and faster, and at some point, the temperature and pressure get so extreme that hydrogen atoms fuse into helium. Energy floods outward. A star is born. What makes each star different is how much material was in that original cloud. The mass a star is born with determines everything about its life: how hot it burns, how bright it shines, how long it lives, and how it dies. A star born with low mass will burn gently for tens of billions of years. A star born with enormous mass will blaze through its fuel in under 10 million. It will shine hundreds of thousands of times brighter. It will influence everything within light years of its position. And when it finally runs out of fuel, it will face a violent and spectacular end. The question is, what does that end look like? And how large can a star actually grow before it tears itself apart? Picture 2 bonfires. One is small, a campfire built with a few logs. It crackles gently, throws off a warm glow, and it will keep burning for hours. The other is a raging inferno, fed by an entire forest's worth of timber. It roars. It throws heat you can feel from 100 feet away. and it will consume everything it has in a fraction of the time. Stars work the same way. A star born with about the same mass as ours will burn hydrogen at a steady, measured pace. It has enough fuel to last roughly 10 billion years. Ours is currently about halfway through that supply. It was born about 4.5 billion years ago, and it has another 5 billion years or so before things start to change. That is a confirmed estimate based on decades of studying how stars like ours evolve. Now compare that to a star born with 20 or 30 times more mass. This star does not burn slowly. It crushes hydrogen together at a furious rate. Its core temperature is far higher, the pressure is far greater, and the energy output is staggering. A star like this can be hundreds of thousands of times brighter than ours. It lights up entire regions of the galaxy around it. You could see it from unimaginable distances. But there is a cost. That massive star will burn through its hydrogen in about 5 to 10 million years. That sounds like a long time. It is not. Compared to the 10 billion year lifespan of a star like ours, it is a blink, a brief, furious flash, and when that fuel runs out, something dramatic happens. The core of the star has been fusing hydrogen into helium for millions of years. Once the hydrogen in the core is gone, the fusion stops. The outward pressure that had been holding the star up against its own gravity disappears. The core begins to collapse inward. But the story is far from over. In fact, it is just beginning. As the core shrinks, it heats up. The temperatures climb so high that the hydrogen in a shell around the core ignites. This new source of energy pushes the outer layers of the star outward. The star begins to expand. Its surface cools as it stretches wider and wider, shifting from white or blue to orange, then to deep red. The star is growing, and depending on how massive it was at birth, it does not stop for a very long time. A star born with moderate mass might expand to dozens of times its original width. That is the red giant category. A star born with extreme mass can swell to hundreds, or even over 1,000 times its original width. These are the red supergiants, the very stars we are going to visit one by one as they get progressively larger and more extreme on our journey through the galaxy. What makes this important for us is something you might not expect. The elements inside these dying, expanding stars are the same elements that make up everything you see around you: carbon, oxygen, nitrogen, iron. All forged inside stars during this process and scattered across space when those stars finally die. The calcium in your bones was made inside a massive star that died before our solar system even existed. That is confirmed science, supported by decades of spectroscopic observation and nuclear physics. Every heavy element on Earth was cooked inside a star and delivered here by an ancient explosion billions of years ago. So when we look at these giant, bloated, dying stars, we are looking at factories, the very machines that built the ingredients for planets, oceans, and life itself. Now, what happens when one of these giants reaches the end of the line? There is an exact moment when everything changes inside a star. For millions or billions of years, the core has been locked in a battle. Gravity pulls inward, trying to crush the star into a tiny point. The energy from nuclear fusion pushes outward, keeping the star inflated and stable. These two forces hold each other perfectly in check. The star stays balanced. It shines. It lives. Then the hydrogen in the core runs out. Fusion slows. The outward pressure drops, and gravity, which has been waiting patiently all along, begins to win. The core starts to collapse. It compresses. It heats up. Temperatures inside the shrinking core climb to hundreds of millions of degrees, and at that new, extreme temperature, something unexpected kicks in. Helium, the leftover ash from hydrogen fusion, starts to fuse. Helium atoms are heavier and harder to push together. It takes far more energy to ignite them than it took for hydrogen. But the collapsing core generates enough heat and pressure to get the job done. Helium fuses into carbon, carbon fuses into oxygen. Each new reaction releases a burst of energy, which temporarily halts the collapse and keeps the star alive a little longer. This is where the star's mass becomes the ultimate judge. If the star started with a low mass, like ours, the helium fusion happens in a dramatic flash. The core reignites violently, stabilizes, and the star settles into a new phase of life. It expands into a red giant, but it never gets the heat or pressure needed to fuse anything heavier than carbon and oxygen. Eventually, its outer layers drift away gently, leaving behind a dense, cooling core called a white dwarf, a quiet death, a slow fade into darkness. But for stars that started with 8 times our star's mass or more, the story goes much further and much darker. These massive stars do not stop at carbon and oxygen. Their cores are heavy enough, hot enough, and under enough pressure to keep going. Carbon fuses into neon. Neon fuses into oxygen. Oxygen fuses into silicon. And silicon fuses into iron. Each stage happens faster than the one before it. Hydrogen burning lasted millions of years. Helium burning lasts a few 100,000 years at most. Carbon burning might last a few 100 years. And when the star reaches silicon, it burns through that entire supply in just a single day, sometimes even less. Scientists have confirmed this accelerating timeline through detailed computer models of stellar evolution. Iron is the end of the road. When you try to fuse iron, the reaction does not release energy. Instead, it absorbs it. The core suddenly has no way to push back against gravity. Nothing left to burn. In less than a second, the core collapses at nearly a quarter of the speed of light. The outer layers come crashing down behind it. They slam into the impossibly dense, collapsing core and bounce off in a catastrophic explosion. A supernova. For a brief moment, that single dying star outshines its entire galaxy. Billions of stars, all dimmer than this one explosion. The energy released is so enormous that it creates every element heavier than iron. Gold, silver, platinum, uranium, all forged in that instant of destruction and scattered into space. What remains depends on the original mass. A lighter, massive star leaves behind a neutron star, a ball of matter so dense that a teaspoon of it would weigh over 1 billion tons. A heavier one collapses beyond even that, forming a black hole. But before any of that happens, the star goes through a phase that is critical for our journey, the bloated, swollen, dying phase, the red supergiant phase. That is where the truly enormous stars live. And the first one on our path is closer than you might think. Imagine inflating a balloon inside a room. You blow air into it. It grows. The rubber stretches thinner and thinner. The surface gets cooler to the touch as the material spreads out. And if you keep pumping air, eventually the balloon fills the entire room, pressing against the walls, the ceiling, the floor. That is roughly what happens when a dying star becomes a red giant. When the hydrogen in a star's core runs out and the core begins to contract, the layers above the core respond in a surprising way. Instead of collapsing inward, they push outward. The intense heat from the shrinking core ignites hydrogen in a shell around it. This shell burning generates an enormous amount of energy. That energy presses against the outer layers of the star and forces them to expand. The star starts to grow rapidly. A star that was once compact, maybe 1 million miles across, begins to stretch. Its outer layers puff out to tens of millions of miles, then hundreds of millions. The surface temperature drops because that same energy is now spread across a vastly larger area. The star that once glowed white or yellow cools to a deep orange, then to a dark red. This is why they are called red giants. They are red because they are cooling, and giant because they are expanding far beyond their original boundaries. For a star like ours, this red giant phase will swell its outer edge to roughly the orbit of Mars, about 140 million miles from where the core sits. Everything inside that radius will be consumed. Mercury, Venus, and Earth will be inside the star. That is confirmed. Stellar evolution models have calculated this outcome with high precision. When our star runs out of core hydrogen in roughly 5 billion years, it will inflate into a red giant and engulf the inner planets. But wait, the numbers get much more extreme. For heavier stars, the expansion goes far further. A star born with 15 or 20 times the mass of ours does not just become a red giant, it becomes a red supergiant. These objects stretch to hundreds, sometimes over 1,000 times the width of our star. Their surfaces extend to distances that would reach past the orbit of Jupiter, or even further out towards Saturn. And what makes them unsettling is how thin they are at the edges. The outer layers of a red supergiant are incredibly diffuse. The gas at the surface is far less dense than the best vacuum we can create in a laboratory on Earth. You could fly a spaceship through the outer layers of a red supergiant and barely notice you were inside a star. The gas would be thinner than the space between molecules in a sealed chamber on Earth. Yet the star is still there, glowing, red, stretching across the sky like a vast, ghostly sphere. These stars are unstable. Their outer layers pulse and wobble. They shed material into space at terrifying rates. Some red supergiants lose enough mass every year to build entire planets from the discarded gas. The space around them fills with clouds of expelled dust and molecules, creating enormous shells that can stretch light years across. And all of this is happening on a clock. The red supergiant phase does not last long. For the most massive stars, it may persist only a few 100,000 years before the core finally collapses and the star explodes in a supernova. Right now, somewhere in the Milky Way, a red supergiant is in its final days. It could go off this year, this decade, this century. We simply do not know which one will be next. The first stop on our tour is a familiar star, one that has already begun its transformation, and 5 billion years from now, it will demonstrate exactly what this process looks like from terrifyingly close range. 5 billion years from now, something will go wrong. Our star will run out of hydrogen in its core. The fusion that has kept it stable for over 10 billion years will stutter and fail. The core will begin to shrink, and the outer layers will start to swell. At first, the changes will be slow. Over hundreds of millions of years, our star will gradually brighten. Its surface will creep outward. Earth's average temperature will start to climb. The oceans will warm, then they will begin to evaporate. Slowly at first, then faster, until the entire surface of our planet is a scorched, dry wasteland. Every river, every lake, every ocean, gone. But the dying star will not stop there. As the expansion continues, our star's outer edge will push past the current orbit of Mercury. That planet will be absorbed, swallowed into the star's bloated body without a trace. Venus goes next, engulfed, vaporized, inside the expanding shell of superheated gas. And then it reaches us. There is still debate among scientists about whether Earth will be physically swallowed, or whether it will spiral outward as our star loses mass. Some models suggest that as the star sheds material during its expansion, the gravitational pull weakens, and Earth's orbit might widen just enough to escape being consumed. Other models say the drag from the star's expanding atmosphere will slow Earth down, pulling it inward to be destroyed. Either way, it does not matter much for life. Long before the surface of the star arrives, Earth will be uninhabitable. The heat will have stripped away the atmosphere. The surface temperature will climb to thousands of degrees. Every trace of life, every city, every fossil, every footprint left by every creature that ever lived on this planet will be erased. This is confirmed science. We know this will happen because we can see it happening to other stars right now. All across the galaxy, stars similar to ours are going through this exact process. We can observe them in various stages of expansion and decay. The evidence is overwhelming. Our star will eventually reach its maximum size as a red giant. At its largest, it will stretch roughly 150 million miles from its core. That is close to where Earth orbits today. After that peak, the outer layers will slowly drift away into space, forming a beautiful, glowing cloud of gas called a planetary nebula. The core left behind will be a white dwarf, a dense ball of carbon and oxygen about the size of Earth, slowly cooling over trillions of years until it fades to black. That is how our star dies, quietly, gently, a long fade into darkness. But our star is small. Remember that. Stars that are 8, 10, 20 times more massive face a completely different fate. They do not fade quietly. They do not cool gently into white dwarfs. They burn hotter, they expand further, and they grow to sizes that make our star's red giant phase look tiny by comparison. And when they finally die, they do it with an explosion that can briefly outshine an entire galaxy of hundreds of billions of stars. Those are the stars we are heading toward now, the red supergiants, the monsters. And the difference between a red giant and a red supergiant is staggering. Same basic process, where a dying star expands outward as its core contracts. Completely different scale. Think of it as the difference between a pond ripple and a tsunami. Both are waves. One barely moves the water, the other reshapes coastlines. The first true giant on our path is a star you can actually see in the night sky. It is 25 times wider than ours, glowing bright orange, and hurtling through the Milky Way at an incredible speed. Its name is Arcturus. There is a line in the life of a star where everything changes. Below a certain mass, a star dies quietly. It swells into a red giant, sheds its outer layers, and leaves behind a white dwarf, peaceful, slow, like a candle burning down to nothing. Above that line, the death is violent. The star becomes something far more extreme, larger, brighter, more unstable. And its end comes with an explosion that seeds the universe with the building blocks of everything. That dividing line sits at roughly 8 times the mass of our star. Any star born below that threshold will follow the path we just described. It will fuse hydrogen, then helium, and stop there. The core will never get hot enough to ignite carbon. The outer layers will drift away peacefully, and the dense core will cool for eternity. But a star born above 8 times the mass of ours enters a different category entirely. Its core burns hotter. It fuses heavier elements, one after another. And its outer layers do not just expand into a red giant. They keep going. They swell to sizes that would fill the inner solar system, the outer solar system, and beyond. This is where red supergiants are born. A red supergiant is a massive star in the final phase of its life. Its core is actively burning through heavier and heavier elements, racing toward the iron wall that will trigger a supernova. Meanwhile, its surface has expanded to staggering dimensions, hundreds of times the width of our star, sometimes over 1,000. The key difference between a red giant and a red supergiant is mass and scale. A red giant might be 50 to 100 times the width of our star. Large, yes. Impressive, absolutely. But a red supergiant can be 10 times larger than that. The jump between the two categories is enormous. And there is something else. Red supergiants are rare. The conditions needed to create one require a very large initial mass, and massive stars are uncommon. For every red supergiant in the galaxy, there are thousands of smaller, quieter stars living out their unremarkable lives. Supergiants are the exceptions, the outliers, the freaks, yet they matter more than almost anything else in astronomy. Here is why. When a red supergiant finally explodes, the supernova does 2 things that shape the entire universe. First, it scatters all the heavy elements that were forged inside the star. Carbon, oxygen, silicon, iron, these elements mix with nearby clouds of gas and dust. New stars form from those clouds. Planets form around those stars. And on some of those planets, the heavy elements become the foundation for chemistry, geology, and life. Second, The shock wave from the explosion compresses nearby gas clouds, triggering the birth of new stars. Supernovae are both destroyers and creators. They end one star's life and spark the beginning of others. Without them, the universe would be nothing but hydrogen and helium. No rocky planets, no liquid water, no carbon-based life. Every atom in your body, heavier than helium, was produced by a star that went through this exact process. That is one of the most confirmed facts in all of astrophysics. We exist because massive stars lived, expanded into red supergiants, and died in explosions. And the bigger the star, the more dramatic everything becomes. Larger supergiants produce more powerful supernovae. They forge heavier elements. They influence wider regions of the galaxy. So as we travel deeper into this journey, the stars will get bigger, the numbers will get harder to believe, and the consequences of their existence will feel more and more personal. Our next stop is Arcturus, a real, visible star in our night sky, 25 times wider than ours, already old, already dying, and compared to what comes later, it is tiny. Look up on a clear spring night, and you will find it. Follow the curve of the Big Dipper's handle, arc it outward, and you will land on one of the brightest stars in the entire sky, a glowing orange point of light about 37 light-years from Earth. That star is Arcturus. It is close. In astronomical terms, it is practically in our backyard, and it is one of the easiest examples of what happens when a star like ours grows old. Arcturus is roughly 25 times wider than our star. If you placed it where ours sits, its surface would extend about halfway to Mercury's orbit. It is also about 170 times more luminous. That means it pumps out 170 times more total energy. You would feel the difference. But here is what makes Arcturus interesting beyond its size. This star was not always a giant. Billions of years ago, Arcturus was a fairly normal star. It was slightly more massive than ours, burning hydrogen at a steady rate. It lived quietly for a very long time. Then, like all stars eventually do, it burned through its core hydrogen and started to change. The core contracted, the outer layers expanded. Arcturus became a red giant. This is the same process that will happen to our star in 5 billion years. Arcturus is showing us our future, right now, in real time, and it is moving fast. Arcturus travels through the Milky Way at a remarkable speed. It crosses the sky faster than almost any other bright star, covering roughly the width of a full moon in about 800 years. Scientists have confirmed that Arcturus does not belong to the same population of stars as ours. It comes from an older, different group. It was likely born in a smaller galaxy or star stream that was absorbed into the Milky Way billions of years ago. It is a visitor, passing through our neighborhood on its way to somewhere else. That means the star you see when you look at Arcturus was not always here, and it will not stay. In a few million years, it will have moved so far that it will no longer be visible to the naked eye from Earth. Future generations will never see it. Right now, though, it is brilliant. The fourth brightest star in the entire night sky, a glowing testament to what aging does to a star. Inside Arcturus, the core is now fusing helium into carbon and oxygen. This phase of life is shorter and more intense than the hydrogen burning phase. Arcturus will not stay a red giant forever. Eventually, its outer layers will peel away, drifting into space as a gently expanding cloud. What remains will be a dense, hot core, a white dwarf, and the light of Arcturus will slowly fade from the galaxy, but that ending is far away. Right now, Arcturus is alive and swollen. Its surface temperature is about 7,500 degrees Fahrenheit, cooler than our star's roughly 10,000 degrees. That lower temperature is what gives it the deep orange color. Cooler stars glow red and orange. Hotter stars glow white and blue. Arcturus falls right in the orange zone, which makes it a dramatic and beautiful sight through a telescope. For humanity, Arcturus has been a landmark for thousands of years. Ancient Polynesians used it for navigation across the Pacific. The name itself comes from the ancient Greek word for guardian of the bear, because it appears to follow the constellation Ursa Major across the sky. We have admired it, studied it, and used it to find our way, and it is just the beginning of what we are going to see. 25 times the width of our star sounds impressive. It is, compared to anything on Earth, it is beyond enormous. However, in the catalogue of giant stars, Arcturus is modest, a warm-up, a starting point, because the next star on our journey is already bigger, angrier, and sitting only 65 light-years away, staring at us with a deep, glowing, red eye. 65 light-years from Earth, a star burns a deep orange-red. It sits in the face of Taurus, the bull. For thousands of years, cultures around the world have looked at this star and called it the Eye, the angry, glowing eye of a celestial beast. The ancient Persians considered it one of the 4 royal stars of the heavens. The name Aldebaran comes from the Arabic word for the follower, because it appears to chase the Pleiades star cluster across the sky. It is beautiful. It is also dying. Aldebaran is a red giant, roughly 44 times wider than our star. That is nearly double the size of Arcturus. If you could drop Aldebaran into the center of our solar system, its surface would stretch roughly to the orbit of Mercury. Everything inside that boundary would be enveloped. It shines with about 400 times the luminosity of our star. That enormous energy output is what makes it so visible despite sitting 65 light-years away. To the naked eye, it is one of the brightest stars in the winter sky, glowing with that signature orange-red warmth that makes it unmistakable. But here is where the science gets revealing. Aldebaran has already finished burning hydrogen in its core. The hydrogen is gone. The core is now contracting, heating up, and fusing helium into carbon and oxygen. This process is confirmed through spectroscopic analysis, where astronomers study the light coming from the star to determine what elements are present and what reactions are taking place. The helium burning phase will not last nearly as long as the hydrogen phase did. Aldebaran does not have many millions of years left as a giant. Eventually, the helium in the core will be exhausted too. At that point, the outer layers will begin to peel off, and the star will shed its skin into space. What is fascinating about Aldebaran is how close it is to us, and how clearly we can study it. In 2017, astronomers pointed the Hubble Space Telescope at this star during a rare event. The asteroid named Leona passed in front of Aldebaran, briefly blocking part of its light. Events like this, called occultations, allow scientists to measure a star's diameter with extreme precision by tracking exactly how the light dims and reappears. These observations confirmed Aldebaran's diameter at roughly 44 times that of our star, give or take a small margin. This kind of direct measurement is rare. For most giant stars, size estimates rely on models and indirect calculations. With Aldebaran, we have hard data. That makes it one of the best studied red giants in the sky. And yet, there is something about Aldebaran that most people overlook. It has a companion, or at least, it might. For decades, astronomers tracked tiny wobbles in Aldebaran's motion that suggested a massive planet was orbiting it. In 2015, a study reported evidence of a gas giant roughly 6 times the mass of Jupiter, orbiting Aldebaran at about the same distance that Mars orbits our star. But later studies cast doubt on this. The wobble might have been caused by the star's own pulsations, not a planet. As of now, the existence of Aldebaran's planet remains uncertain. It is a mystery that future observations might resolve. What is certain is this: Aldebaran represents the next step on our scale, larger than Arcturus, hotter in output, already deep into its final evolutionary phase. A star that has moved well beyond the prime of its life and is racing toward its end, 44 times the width of our star, visible to anyone on Earth who looks up in winter, and still Compared to what lies ahead, this is small, because the next star on our journey takes the concept of a dying giant and pushes it in a direction you might not expect. It does not just expand, it bleeds. At the bottom of the Southern Cross, there is a star glowing deep red. You cannot see it from most of the northern hemisphere, but for anyone south of the equator, it is one of the most recognizable stars in the sky. It marks the base of Crux, the smallest constellation, and it has been used for navigation across the southern oceans for centuries. Its name is Crux, and it is doing something remarkable. Crux is a red giant, roughly 84 times wider than our star. That puts it nearly twice the size of Aldebaran. It sits about 88 light-years from Earth, close enough for astronomers to study in detail. But what makes this star special is its chemistry. Crux is a carbon star. Deep inside its core, nuclear fusion has been creating carbon through the triple alpha process, where 3 helium atoms fuse together to form one carbon atom. This is a confirmed nuclear reaction well understood in stellar physics. The unusual part is what happens next. In certain red giants, a process called dredge up occurs. Powerful convection currents inside the star reach deep into the interior, grab freshly forged carbon, and carry it all the way up to the surface. The carbon then gets mixed into the star's outer atmosphere. Some of it escapes entirely, carried away by the star's stellar wind into the surrounding space. Crux is literally leaking carbon into the galaxy. Think about what that means. Carbon is one of the most important elements for life. It forms the backbone of every organic molecule. Your DNA, your proteins, the sugar in your blood, all of it built on carbon atoms. And here is a star dumping that very element into the interstellar medium, where it can eventually become part of new stars, new planets, and possibly new life. This process is happening across the Milky Way right now. Thousands of carbon-rich giant stars are shedding their atmospheres into space, seeding the galaxy with one of life's most essential ingredients. Scientists have confirmed that a significant portion of the carbon in the universe was produced and distributed exactly this way. And if you could somehow see Crux's stellar wind, it would be haunting. Imagine streams of dark, sooty material drifting away from the star in slow, spiraling ribbons. Carbon dust particles, each one smaller than a grain of sand, floating outward into the void. Over time, these particles mix with hydrogen gas clouds. Those clouds collapse, form new stars, and the carbon becomes part of new worlds. The cycle continues. Now, Crux itself is nearing the end. Like Aldebaran, it has already exhausted the hydrogen in its core and is working through heavier elements. Its outer layers are cooling. Its surface pulses gently, growing slightly larger, then contracting, then growing again. This pulsation has been measured at a period of roughly 2 weeks, which is extremely short for a giant star. Some scientists believe that Crux may be approaching a transition. As it continues to shed its outer layers, it will eventually lose enough mass to expose its core. The remaining envelope of gas will float away as a planetary nebula. The hot core underneath will become a white dwarf, rich in carbon and oxygen, a diamond the size of a planet, slowly cooling forever. That image is striking, but what is more important for our journey is the scale. 84 times the width of our star, larger than anything we have discussed so far, actively shedding elements that are essential for life. And still, by the standards of what comes next, Crux is modest. Because we are about to leave the realm of red giants entirely and enter the territory of the supergiants. Before we do, though, there is something we need to talk about. Something that affects every measurement, every size estimate, and every claim about giant stars. Something that makes this whole journey much harder than you might expect. We need to talk about how astronomers measure something they can never touch. Here is the problem. Stars are far away. The closest one beyond our own is over 4 light-years from Earth. That is more than 23 trillion miles. You cannot send a ruler. You cannot walk up to a star and wrap a tape measure around it. Everything we know about the size of a distant star comes from indirect methods, clever tricks, calculations built on other calculations, and every one of those methods has limits. The most direct way to measure a star's size is something called interferometry. This involves combining the light collected by 2 or more telescopes that are separated by a large distance. By analyzing how the light waves from those telescopes interact with each other, scientists can determine the angular diameter of a star. That is how wide the star appears in the sky, measured in tiny fractions of a degree called milliarc seconds. Think of it this way. If you hold a penny at arm's length, it covers about half a degree of the sky. A milliarc second is about 1.8 million times smaller than that. These are incredibly tiny angles, and measuring them requires extraordinary precision. Once you know the angular diameter, you combine it with the star's distance to calculate the actual physical size. Simple geometry. But both of those numbers, the angle and the distance, carry uncertainty. A small error in either one can change the final size estimate dramatically, and that is where things get tricky. Distances to stars are hard to pin down, especially for very far objects. The main tool astronomers use is parallax, where they measure how much a star appears to shift in position as Earth orbits our star. Close stars shift more, distant stars shift less. The European Space Agency's Gaia spacecraft has been mapping these shifts for billions of stars with unprecedented accuracy, but even Gaia has limits. Stars beyond a few thousand light-years often have distance uncertainties of 10, 20, or even 50%. For the biggest stars, the problem gets worse. Red supergiants are surrounded by thick clouds of dust and gas. This material absorbs and scatters light, making the star appear dimmer and sometimes even a different color than it truly is. Astronomers must account for this, and the corrections introduce more uncertainty. Also, red supergiants pulse. They change size. A star measured during a maximum expansion phase might appear much larger than the same star measured 6 months later. There is also the question of where a star's surface actually is. Our star has a relatively clear boundary. The photosphere, where light escapes, is well defined. Red supergiants do not have this luxury. Their outer atmospheres are so diffuse, so extended, that there is no hard edge. The star gradually fades into the surrounding space. Deciding where the star ends and the void begins is a judgment call, and different methods can give different answers. This is why the title of largest star keeps changing. New measurements come in. Distances get revised. The border of a star's atmosphere gets redefined. A star that was once called the largest in the universe might be reclassified as merely very large when better data arrives. We will see this happen multiple times on our journey. Stars that held records for years, dethroned overnight by a single new study. So when you hear a number like 1,000 times wider or 2,000 times wider, know that these are best estimates. They are based on the best data available at the time, but they carry real uncertainty. Science is honest about that. The error bars are part of the story. With that understanding, we can move forward with confidence. We know how the measurements work. We know where the uncertainty lives. And we are ready to meet a giant that has a confirmed planet still orbiting around it. 34 light-years away, there is a giant star with a planet. That might not sound extraordinary at first. We have found thousands of planets orbiting other stars, but most of those planets orbit relatively normal, stable stars in the prime of their lives. Finding a confirmed planet around a giant star that has already left the main sequence is rare, and it raises a question that should make you pause. What would it be like to stand on that world? Pollux is the brightest star in the constellation Gemini, the twins. It is an orange giant, roughly 9 times wider than our star. That makes it smaller than Aldebaran or Gacrux, but it earns its place on this journey for a different reason. In 2006, astronomers confirmed the existence of a planet orbiting this star, designated Pollux B. Later, through a public naming campaign, the planet was given the name Thestius. This is a confirmed discovery. The planet was detected using the radial velocity method, which tracks tiny wobbles in a star's motion caused by the gravitational tug of an orbiting body. The data is solid. Thestius is real. It is a gas giant, estimated at roughly 2.5 times the mass of Jupiter. It orbits Pollux at a distance of about 107 million miles, which is slightly farther than Earth orbits our star. The orbital period is about 590 days. Now, imagine standing on a hypothetical moon orbiting Thestius, looking up at the sky. Pollux would dominate your view, because the star is 9 times wider than ours, but the planet orbits at a similar distance. The star would appear vastly larger in the sky than our star does from Earth. It would be a massive, warm, orange disk, filling a significant portion of the horizon. The light would be softer, more orange, and the shadows it cast would have a warm tint. Astronomers believe this system has been stable for a very long time, but it will not last. Pollux is continuing to evolve. As it exhausts the helium in its core, it will expand further. Its luminosity will increase. The habitable zone around it, the region where liquid water could exist, has already shifted outward, and eventually, the expanding star might threaten the orbit of Thestius itself. This is something we rarely think about. When we search for planets around other stars, we usually focus on young, stable systems. We look for Earth-sized worlds in comfortable orbits around quiet stars. But the universe is full of planets orbiting dying giants, worlds that once had stable conditions and are now watching their star swell, redden, and slowly consume the space around them. Thestius is living through that process right now. What makes Pollux valuable for our journey is perspective. It is close enough to study in detail. It has a confirmed planet, and it shows us that giant stars are not just distant, abstract objects. They are real places with real worlds around them. Worlds that are affected by their stars' aging and expansion in ways that reshape entire solar systems over long stretches of time. There is also something poetic about it. Pollux and its twin, Castor, have been watched by humans since ancient times. The two stars of Gemini, side by side, but they are very different. Castor is actually a complex system of 6 stars bound together. Pollux is a solitary giant with a planet, 2 twins that could not be less alike. Pollux is relatively small, as giants go, 9 times wider, bright, but nothing extraordinary compared to the monsters waiting ahead. And that is exactly the point, because we are about to leave the comfortable range of ordinary giant stars and step into a completely different category, a place where size and brightness stop following the same rules, where a star can outshine ours by 100,000 times, yet glow blue instead of red, where youth and violence replace old age and slow decay. That star is one of the most famous in the sky, and it is younger than most of the mountain ranges on Earth. Before we go further, we need to clear up something that confuses almost everyone. The biggest star is not always the brightest. The brightest star is not always the biggest. Size and brightness are 2 different measurements, and understanding the difference will change how you see everything from this point forward. Brightness in astronomy is called luminosity. It measures the total amount of energy a star produces every second. A star with high luminosity is pumping out enormous amounts of light, heat, and radiation. A star with low luminosity is dim and quiet. Size is simpler. It is the physical width of the star, how far its surface extends from the center. Here is where it gets strange. A small, compact star can be incredibly luminous if it is hot enough. Temperature is the hidden variable. A star's surface radiates energy based on how hot it is. Hotter surfaces radiate far more energy per square foot than cooler surfaces, so a small, extremely hot star can easily outshine a much larger, cooler one. This follows a relationship that physicists call the Stefan-Boltzmann law. It states that the energy radiated by a surface goes up with the fourth power of its temperature. That means if you double the temperature, the energy output does not just double, it increases by a factor of 16. This is why blue and white stars, which are much hotter, can be far more luminous than red giants that are many times their size. A red supergiant might be 1,000 times wider than a blue supergiant, but if the blue star's surface is 3 or 4 times hotter, the blue star might actually produce more total energy. This concept matters enormously for our journey. The stars we have been visiting so far are large because they expanded as they aged. Their surfaces cooled down. They glow red or orange because of that lower temperature. They are impressive in size, but their luminosity per unit of surface area is relatively modest. The stars we are about to meet break that pattern. Some of them are enormous and incredibly luminous, and some of them are not that large at all, yet they outshine almost everything in the galaxy. Take a young, massive blue star. It might be only 10 or 15 times wider than ours. In the catalogue of giant stars, that is nothing special, but it could be burning at 50,000 degrees on its surface, making it ferociously bright. These stars can produce hundreds of thousands of times the energy of our star while being physically much smaller than a red giant. Then consider a red supergiant. It might be 800 times wider than our star. Absolutely massive. But its surface temperature is only around 6,000 degrees Fahrenheit. Each square foot of its surface produces far less energy than the blue star. The red supergiant compensates for this with sheer size. Spread 6,000 degrees across a surface that stretches hundreds of millions of miles, and the total output adds up. The result is that both stars can have similar total luminosities for completely different reasons. One is small and hot, the other is huge and cool. Same total brightness, completely different physics. This also explains why astronomers care so much about measuring both size and temperature when they study a star. One number alone tells you almost nothing. You need both to understand what is really going on. A star that looks dim might actually be enormous if it is far away. A star that looks tiny might be pumping out more energy than an entire cluster of red giants. Understanding this distinction is critical because the next star we visit is a perfect example. It is not a giant. It is not a red supergiant. It is a blue supergiant, one of the most luminous stars within 1,000 light-years of Earth. And it demonstrates that in the world of stars, raw physical size is only half the story. The real power often hides in the temperature. Look at Orion on a winter night, and you will see two stars that could not be more different. One glows orange-red in the upper left. That is Betelgeuse, and we will get to it soon. The other burns a fierce blue-white in the lower right. That is Rigel, and it is one of the most powerful stars within reach of our telescopes. Rigel sits roughly 860 light-years from Earth. Even at that distance, it is the 7th brightest star in our sky. It is the brightest star in the constellation Orion, and it outshines our star by an almost absurd amount. Scientists estimate that Rigel produces roughly 120,000 times the luminosity of our star. That is confirmed through spectral analysis and distance measurements. One star, generating the energy output of 120,000 of ours combined. And here is what makes it fascinating. Rigel is only about 79 times wider than our star. That is smaller than Gacrux, smaller than some of the red giants we already visited. Yet it crushes them all in raw energy output. The reason is temperature. Rigel's surface burns at roughly 21,000 degrees Fahrenheit. That is more than double the temperature of our star's surface and many times hotter than any red giant. At that temperature, every square foot of Rigel's surface is radiating enormous amounts of energy. The blue-white color is a direct result of this extreme heat. Hotter objects glow blue, cooler objects glow red. Rigel is scorching. If you could somehow stand on a planet near Rigel, the light would be blinding, harsh, intensely white with a blue edge. Nothing like the warm yellow glow of our star. Everything would look washed out, overexposed, flooded with ultraviolet radiation that would be lethal within moments. This star is also young, incredibly young. Rigel is estimated to be only about 8 million years old. For comparison, our star is over 4 billion years old. Rigel has existed for less than 0.1% of our star's lifetime. It was born long after the dinosaurs went extinct, long after mammals took over the planet. In cosmic terms, Rigel is a newborn, yet it is already nearing the end. Massive stars live fast and die young. Rigel was born with roughly 21 times the mass of our star, and it has been burning through its hydrogen at a furious rate. It has already left the main sequence and begun expanding. Astronomers classify it as a blue supergiant because it is still extremely hot, but it is in a transitional phase. Over the next few 100,000 years, it may cool and expand further, possibly becoming a red supergiant before exploding as a supernova. That explosion would be spectacular from Earth's distance. Rigel is far enough away that we would be safe, but it would become one of the brightest objects in the sky for weeks. What matters for our journey is the lesson Rigel teaches. Power does not require enormous size. This star is relatively compact by supergiant standards, yet it dominates its region of the galaxy. It illustrates that mass, temperature, and luminosity are the true measures of a star's impact, not just how wide it stretches. But we are on a journey about size. And Rigel, as impressive as it is, points us towards something bigger. Because there are stars in the galaxy that combine the extreme luminosity of a blue furnace with the extreme size of a red supergiant. Stars that are both huge and blindingly bright. They are rare, they are unstable, and they do not live long. Rigel reminds us that the universe rewards extremes. The hottest stars, the most massive stars, the fastest burning stars, all of them produce effects that ripple far beyond their own neighborhoods. The next one on our path sits so far away that the light we see from it tonight left the star before many ancient civilizations on Earth were born. If you look up in the northern hemisphere during summer or autumn, you will see a bright white star near the top of a large cross-shaped pattern in the sky. That is Deneb, and its distance from Earth is part of what makes it remarkable. Most of the bright stars you see at night are relatively close. Sirius is about 8.5 light-years away. Vega is 25. Arcturus is 37. These stars appear bright because they are nearby. Deneb is different. It sits roughly 1,500 light-years from Earth. Some estimates place it closer to 2,400. The exact distance remains uncertain because it is so far away that even the best parallax measurements struggle with it. But regardless of which estimate you use, the conclusion is the same. Deneb is extraordinarily far away for a star that is this visible. And yet, it shines as one of the brightest stars in our sky. It forms one corner of the Summer Triangle, a major landmark for stargazers. It is the brightest star in the constellation Cygnus. The only way a star can appear this bright from this far away is if it is producing a staggering amount of energy. And Deneb is. Estimates place its luminosity at roughly 100,000 to 200,000 times that of our star. This makes it one of the most intrinsically luminous stars visible to the naked eye. If Deneb were placed at the same distance as Sirius, it would be bright enough to cast sharp shadows at night. It would dominate the sky like a small lamp, far outshining every other star and every planet. You could comfortably walk through a forest at night using nothing except the light from a single star. The fact that Deneb is so bright, despite sitting so far away, is a testament to its raw, almost reckless power. Deneb is a blue-white supergiant, roughly 200 times wider than our star. That is significantly larger than Rigel, and it burns at a surface temperature of around 15,000 degrees Fahrenheit. It is massive, estimated at roughly 19 times the mass of our star, and like Rigel, it is young and burning through its fuel at an incredible rate, and it will not last. Deneb is expected to end its life in a supernova within a few million years. That is a confirmed prediction based on its mass and evolutionary stage. When it goes, the explosion will be visible from Earth, though at 1,500 light-years or more, we will be safely out of range of any harmful effects. But here is something worth thinking about. The light you see from Deneb tonight left the star around the time the Western Roman Empire was beginning to fracture. When those photons started their journey, most of Europe was entering the early Middle Ages. The entire history of the modern world has played out in the time it took that light to reach your eyes. And somewhere, 1,500 light-years from here, that light is still being produced. Deneb is still burning, still massive, still pouring energy into space at an almost incomprehensible rate. This is what makes deep sky astronomy feel personal. The light is old, the distances are vast, and the stars you see are frozen in a moment of their past. Deneb might already be entering a new phase. It might be swelling into a red supergiant right now. We would not know for centuries. What we do know is that Deneb is a stepping stone. It represents the upper end of blue-white supergiants, stars that are both enormous and ferociously bright. From here, we pivot back toward the red end of the spectrum, because the next star is one of the widest objects you can see without a telescope, and it has a name that means rival of Mars. On a summer night, look low toward the southern sky. You will find a bright star glowing deep red-orange, sitting in the curved body of Scorpius. It pulses with a warm, almost threatening light. Ancient Greeks noticed that its color and brightness resembled the planet Mars, which often passes near it. They named it Antares, meaning rival of Ares, the Greek name for the god of war. It has been a beacon in the sky for thousands of years, and it is one of the true giants. Antares is a red supergiant. Its estimated radius is roughly 700 times that of our star. If you placed Antares at the center of our solar system, its surface would stretch past the orbit of Mars and approach the asteroid belt. Mercury, Venus, Earth, and Mars would all be inside the star. That is a confirmed measurement based on interferometric observations using the Very Large Telescope in Chile. Multiple studies have placed Antares in this size range, making it one of the most reliably measured red supergiants in the sky. If light traveled around its equator, the trip would take over 4 hours. For comparison, light circles our star in just 14.5 seconds. It sits approximately 550 light-years from Earth, close enough for detailed study, far enough that we are safe from anything it might do, and it is doing something alarming. Antares is losing mass at an extraordinary rate. Its stellar wind carries material away from the surface at high speed, creating a vast, expanding shell of gas around the star. Observations have revealed that this shell extends far beyond the visible surface, with material detected at distances equivalent to several times the star's own radius. In 2017, astronomers used the Atacama Large Millimeter Array to map the atmosphere of Antares in unprecedented detail. They discovered that the gas above the star's surface was far hotter than models predicted. Temperatures in the upper atmosphere reached thousands of degrees, higher than the surface itself, which was unexpected for a red supergiant. The cause of this extra heating remains an open mystery. Scientists have proposed convection, magnetic fields, and shock waves as possible explanations, but nothing has been confirmed. That is a genuine scientific puzzle. We can see the heat, we can measure it, we just cannot explain it yet. Antares is also a binary star system. It has a smaller, hotter companion orbiting at a considerable distance. This companion is a blue-white star, much smaller than Antares itself, and it illuminates the gas expelled by its giant partner, creating a faint greenish nebula around the pair. Through a telescope, this nebula is one of the most beautiful sights in the sky. The mass of Antares is estimated at roughly 11 to 14 times that of our star. That mass is enough to guarantee a dramatic end. When Antares exhausts its fuel, the core will collapse, triggering a supernova explosion. At 550 light-years, that supernova would be spectacular from Earth. It would be visible during the day and would outshine every star in the night sky for weeks. We are safe at this distance, but the show would be unforgettable. For our journey, Antares marks a threshold, 700 times wider than our star. That is beyond anything a red giant can achieve. This is solidly in supergiant territory, a star so large that it challenges our ability to even picture it. If you could somehow fly across its face at the speed of a commercial jet, the trip would take over 1,000 years. And yet, even at 700 times the width of our star, Antares is far from the largest. We still have a long way to go, because the next star on our path sits in the constellation Orion. It is roughly the same width as Antares. It is even closer to death, and it has already given us a very real scare. There is a star in Orion that scientists believe could explode any day, or in 100,000 years. Nobody knows for sure. Betelgeuse sits about 500 to 700 light-years from Earth. The exact distance is still debated, which is unusual for a star this bright and this well-studied. It marks the upper left shoulder of Orion, glowing with a distinctly orange-red color that makes it easy to spot on any clear winter night. Ancient civilizations, from the Egyptians to the Aboriginal Australians, tracked its changing color over centuries. It is roughly 700 times wider than our star. Some measurements place it as high as 760. If Betelgeuse replaced our star, its surface would extend past the asteroid belt, far beyond the orbit of Mars. It would swallow every inner planet completely. You could fit hundreds of millions of Earths inside it without filling the space. Betelgeuse is also remarkably young, less than 10 million years old. It was born a hot, blue, extremely massive star, likely over 20 times the mass of our star. It burned through its hydrogen supply in a fraction of the time that smaller stars take, and it has already transitioned into the red supergiant phase. This means it has left the main sequence and is now fusing helium and heavier elements in its core. The clock is ticking, and the end will be violent. Betelgeuse will die in a supernova. That is confirmed. Every star of its mass and evolutionary stage ends this way. The core will build up iron, fusion will cease, gravity will win, and the star will collapse and then explode outward with unimaginable force. The only question is when. Estimates suggest somewhere within the next 100,000 years. In astronomical terms, that is soon, terrifyingly soon. In human terms, it could mean tomorrow, or it could mean long after our civilization has vanished from the planet. There is no way to know precisely when the core will reach that final breaking point. Inside Betelgeuse, the conditions are extreme. The core temperature is hundreds of millions of degrees. Heavy elements are being forged and burned in rapid succession, each new fuel source lasting shorter than the one before. The star's surface, meanwhile, is boiling. Literally. Massive convection cells, each one larger than our entire solar system, rise and fall on Betelgeuse's surface. Superheated gas bubbles up from deep inside the star, reaches the surface, cools, and sinks back down. Through telescopes, the surface of Betelgeuse looks lumpy and uneven, constantly churning. This is a star in turmoil, and it shows. Betelgeuse is a semi-regular variable star. Its brightness changes over time in a pattern that repeats roughly every 400 days, though the cycle is messy and unpredictable. Sometimes it brightens noticeably, sometimes it dims. These fluctuations are caused by pulsations in the outer layers, which expand and contract over months. The star breathes, it swells, then it shrinks, then it swells again. each cycle slightly different from the one before. For most of recorded history, these changes were subtle, interesting to astronomers, certainly, but nothing alarming. Then came late 2019. Betelgeuse began to dim dramatically. It lost nearly half its brightness in a matter of weeks. The star that had been one of the top 10 brightest in the sky dropped to a level that was visibly noticeable to anyone who looked at Orion. News headlines around the world asked the same question: is Betelgeuse about to explode? The answer, it turned out, was no, probably not. But what actually happened was almost as fascinating. We will get into that next. Because the great dimming of Betelgeuse revealed something about how these massive dying stars behave that scientists had never directly observed before, and it changed how we think about the final years of a red supergiant. In October of 2019, astronomers noticed something unusual. Betelgeuse was getting dimmer. At first, nobody panicked. Variable stars change brightness all the time. That is what they do. Betelgeuse had faded before and always bounced back, but this time was different. By February of 2020, Betelgeuse had lost roughly 60% of its usual brightness. From Earth, the change was visible to the naked eye. Orion's shoulder, normally one of the most striking features of the winter sky, looked faded, almost sickly. The astronomy community erupted with speculation. Major news outlets ran stories asking if we were about to witness the most spectacular astronomical event in recorded human history. Some scientists urged caution. Others admitted that no one could rule out a pre-supernova event because no one had ever watched a red supergiant in the final days before its core collapsed. We simply did not have enough data to say what the warning signs would look like. Then, by April of 2020, Betelgeuse started to recover. The brightness climbed back to normal levels. The immediate crisis was over, but the question remained: what had caused the dimming? The answer came from the Hubble Space Telescope. Observations revealed that in the months before the dimming, Betelgeuse had expelled a massive cloud of hot plasma from its surface. Think of it as a colossal belch, a bubble of superheated gas many times the size of Earth, erupted from one of the giant convection cells on the star's surface and was launched outward into space. As that cloud of hot material traveled away from the star, it cooled rapidly. When it cooled enough, the gas condensed into solid particles, dust. An enormous, thick cloud of dust formed between Betelgeuse and Earth, blocking a significant portion of the star's light. That was it. Betelgeuse had not entered a pre-supernova phase. It had essentially sneezed, a massive, violent sneeze that ejected enough material to temporarily block its own light from our point of view. Scientists confirmed this explanation through multiple lines of evidence. Ultraviolet observations from Hubble showed the hot plasma being ejected. Infrared observations showed the dust forming, and the timeline matched perfectly. The event was later described as a surface mass ejection, similar in concept to the coronal mass ejections that our own star produces, but on a vastly larger and more violent scale. The Great Dimming taught astronomers several important things. First, red supergiants can undergo sudden, dramatic episodes of mass loss. This was known in theory, but the Betelgeuse event was the first time it was observed so clearly and so close. Second, the ejected dust can noticeably affect the star's brightness as seen from Earth. When we see other red supergiants dimming unexpectedly, it might be the same kind of event. Third, and most unsettling, the event showed how little we understand about the final stages of these massive stars. If a dust cloud can mimic what many people assumed a pre-supernova would look like, then how would we actually recognize the real warning signs? The honest answer is that we might not until it happens. Betelgeuse has not returned entirely to normal since the Great Dimming. Its brightness cycle, once around 400 days, appears to have shortened to roughly 200. And in 2023, it began brightening beyond its usual peak. Something may have shifted permanently inside the star. Scientists are watching closely. When Betelgeuse finally does explode, it will be visible during the day for months. At night, it would be almost as bright as the full moon. A single pinpoint of light, bright enough to read by at midnight. We are not in danger at this distance, but the sight would be something no human being has ever witnessed, and we would lose Orion's shoulder forever. Betelgeuse, as enormous as it is still just the beginning of what awaits us. We are now entering the realm of the true titans, stars that push past 1,000 times the width of our star and keep going. The next one is one of the reddest and most mysterious objects in the sky. Imagine stepping outside one evening and noticing something strange. In the constellation Orion, where the upper left shoulder has always glowed a soft orange-red, there is now a point of light so bright it hurts to look at directly. It is brighter than every other star combined. It is brighter than the planet Venus. It is almost as bright as the full moon, compressed into a single blazing dot. That is what a Betelgeuse supernova would look like from Earth, and scientists have modeled it in detail. The moment the core of Betelgeuse collapses, a shockwave will tear through the star at roughly 10% of the speed of light. The energy stored in the core, accumulated over millions of years, will be unleashed in an instant. Within seconds, the outer layers of the star will be blasted outward in every direction. The energy released in that single explosion will be more than our star will produce in its entire 10 billion year life. All of it. Released in a matter of seconds. From Earth, the first sign would be a burst of neutrinos. These ghostly particles travel at nearly the speed of light and barely interact with matter. They would pass through the planet without anyone feeling a thing. But neutrino detectors around the world, buried deep underground, would light up simultaneously. Scientists would know instantly what had happened. They would have a few hours of warning before the light arrived. Then the sky would change. The light from the explosion would reach Earth, and Betelgeuse would suddenly jump in brightness by a factor of roughly 1,000,000. For weeks, it would be visible during the day. You could look up at noon and see it, a brilliant pinpoint against the blue sky. At night, it would cast faint shadows on the ground, like a distant street lamp. The constellation Orion would be transformed, one shoulder blazing with unnatural intensity, while the rest of the figure stayed the same. Over the following months, the brightness would slowly fade. The expanding cloud of debris would cool and dim. Within a year or two, the new point of light would become a faint smudge, barely visible without a telescope, and the space where Betelgeuse once sat would be occupied by a glowing nebula, a shell of gas and dust expanding outward at thousands of miles per second. Would we be in danger? Almost certainly not. At 500 or more light years, the radiation from the supernova would be far too diluted to cause any harm to Earth's atmosphere or surface. Some studies have calculated that a supernova would need to occur within about 50 light years to pose a serious threat to life on our planet. Betelgeuse is at least 10 times farther than that. What we would lose is the star itself. Orion's shoulder would go dark forever. Thousands of years from now, the nebula left behind would fade, and the space would be empty. One of the most recognizable patterns in the human night sky changed permanently. Astronomers estimate this could happen any time within the next 100,000 years. Maybe sooner, maybe much later. We simply cannot predict when a star's core will reach the exact moment of collapse. But here is what makes this relevant to our journey. Betelgeuse is roughly 700 times wider than our star. It is enormous. It is dramatic. It is famous. And it is still far smaller than the stars we are about to meet. Because the next star on our path makes Betelgeuse look modest. It sits nearly 3,000 light years away, glowing with a deep, blood-red color so intense that one of the greatest astronomers in history gave it a name inspired by precious gemstones. It may be the largest star you can see without a telescope, and it is already being pulled apart from within. Nearly 3,000 light-years from Earth, there is a star that looks like it is bleeding. Its color is so intensely red that when the astronomer William Herschel first observed it in 1783, he called it a deep garnet, comparing it to the rich, dark glow of the gemstone. Ever since, it has been known as the Garnet Star. Its official designation is in the constellation Cepheus, and in 2024, the International Astronomical Union formally approved the Garnet Star as its official name. The color is not decorative. It is a warning, a signal that the star's surface is cooler than most, that its outer layers have expanded to incredible distances, that it is deep into the final phase of its existence. The Garnet Star is one of the largest stars you can see with the naked eye. Its estimated radius falls somewhere between 1,260 and 1,650 times that of our star, depending on which study you reference and which distance estimate you accept. If placed at the center of our solar system, it would stretch past the orbit of Jupiter and possibly reach Saturn. That is larger than Betelgeuse, larger than Antares, larger than almost every star we have discussed so far. It is also one of the most luminous red supergiants in the entire Milky Way. At its most generous estimates, it shines roughly 350,000 times brighter than our star when you include all wavelengths of light, especially the infrared radiation that our eyes cannot see. Much of its energy is invisible to us because it is so cool. Its surface temperature sits around 6,700 degrees Fahrenheit, far below the roughly 10,000 degree surface of our star. That low temperature is what produces the deep red glow. The Garnet Star is surrounded by a shell of ejected material that extends outward from the surface. Infrared observations have revealed a wide ring of dust and water molecules orbiting the star at roughly twice its own radius. This shell was created by the star's intense stellar wind, which carries mass away from the surface at a measured rate. Scientists have confirmed that this star is losing material steadily, shedding its outer layers into space. Inside, the star is nearing the end. It has already exhausted the hydrogen in its core and is believed to be fusing helium into carbon. The clock is ticking toward a supernova. Given its mass, estimated between 15 and 25 times that of our star, the remnant it leaves behind will likely be a black hole. Some scientists even believe the Garnet Star is massive enough to evolve back into a blue supergiant or a Wolf-Rayet star before its core finally collapses. If true, the star would undergo one of the most dramatic transformations in astrophysics, shedding its enormous red envelope to reveal a smaller, hotter, more compact object underneath. That would be a dramatic transformation. A star this enormous, this red, this inflated, shrinking back down, heating up, and turning blue before exploding. It is a theoretical possibility that remains unconfirmed, and if it happens, it would be one of the most extreme evolutionary paths a star can take. The Garnet Star's brightness wobbles over time. It is a semi-regular variable, dimming and brightening with periods near 860 days and 4,400 days. The pulsations cause its outer layers to expand and contract, changing its size by a measurable amount. This breathing behavior is something we see in all the largest red supergiants, and it raises a question that matters for every star on our journey from this point forward. Why do the biggest stars pulse? What is happening inside them to make their surfaces rise and fall like the chest of something alive? If you could watch a red supergiant from close range, sped up 1,000 times, it would look alive. The surface would rise and fall. Massive bubbles of hot gas would swell upward from deep inside the star, reach the surface, cool, and sink back down. The entire outer layer would wobble, expanding outward for months, then contracting, then expanding again. The brightness would fluctuate, the color would shift, the star would look like it was breathing. This is real. It has been observed in multiple red supergiants, including Betelgeuse, the Garnet Star, and many of the stars still ahead on our journey. The pulsation is not random. It follows patterns, though the patterns are messy, irregular, and sometimes change over time. So what causes it? The short answer is instability. Red supergiants exist in a state of constant tension between gravity pulling inward and radiation pushing outward. In a stable star like ours, those two forces balance perfectly, and the star holds a steady size for billions of years. In a red supergiant, the balance is fragile. The outer layers of a red supergiant are enormous and incredibly diffuse. The gas at the surface is spread thin over a vast area. It does not take much to push it around. A small increase in energy output from the interior can cause the outer layers to expand significantly. When they expand, they cool. When they cool, the opacity of the gas changes, meaning the gas becomes more or less transparent to radiation, depending on its temperature and density. This creates a feedback loop. The gas expands, cools, and becomes more opaque. The trapped radiation builds up pressure. That pressure pushes the gas outward further. Eventually, the gas becomes so thin and cool that it becomes transparent again. The trapped radiation escapes, the pressure drops, and the gas falls back inward, only to be heated again and start the cycle over. This mechanism is called the Kappa mechanism, named after the Greek letter used to represent opacity in physics. It is one of the best understood drivers of stellar variability. It is a confirmed process that drives pulsation in many types of variable stars, from smaller Cepheid variables to the massive red supergiants. But in the biggest stars, things get more complicated. Red supergiants also have enormous convection cells on their surfaces. These are rising columns of hot gas, similar to the convection currents in a pot of boiling water, except each cell can be hundreds of millions of miles across. A single convection cell on Betelgeuse can be larger than the orbit of Earth around our star. These convection cells interact with the pulsation. They create hot spots and cool spots on the surface. They cause the star to look lumpy and asymmetric, and they can trigger sudden eruptions of material, like the surface mass ejection that caused the great dimming of Betelgeuse. The combination of pulsation, convection, and mass loss makes red supergiants some of the most unpredictable objects in the sky. No two cycles are exactly the same. The amplitude changes, the period shifts. The surface features rearrange themselves between pulses. Their brightness changes, their size changes, their shape changes. They are not the stable, steady spheres that most people picture when they think of a star. They are chaotic, turbulent, barely holding themselves together. And the bigger they get, the more precarious the balance becomes. And the bigger the star, the worse the instability gets. The next star on our journey is a perfect example. It pulses so violently that its radius swings by hundreds of times the width of our star in a single cycle. Its temperature drops so low at minimum that it pushes the limits of what we thought a supergiant could be. It sits 5,000 light-years away, hidden behind thick clouds of interstellar dust. 5,000 light-years from Earth, behind a wall of interstellar dust, there is a star that refuses to stay the same size. Its name comes from the constellation Sagittarius, where it sits well above the famous teapot pattern. You cannot see it with your eyes. Even at its brightest, it barely reaches the edge of visibility for the most powerful binoculars. But what makes it extraordinary is not its appearance. It is the way it moves. This star pulses with a period of roughly 732 days, nearly 2 full years for a single cycle. Over the course of that cycle, its radius swings between approximately 1,120 and 1,550 times the width of our star. That is a change of over 400 times the width of our star in a single pulsation cycle. The scale of this oscillation is almost beyond imagination. Imagine a sphere hundreds of millions of miles wide, swelling and shrinking by tens of millions of miles every 2 years. At its maximum size, this star would stretch past the orbit of Jupiter if placed in our solar system. At minimum, it pulls back, but it is still enormous. The pulsation changes everything about the star. Its surface temperature swings wildly, dropping as low as roughly 4,500 degrees Fahrenheit at minimum light. That is one of the coldest temperatures ever recorded for a supergiant. Scientists have debated the true nature of this star for decades. Some classify it as a red supergiant or hypergiant, a truly massive star born with enough mass to end in a supernova. Others suggest it might be an extremely large and luminous asymptotic giant branch star, which is a different evolutionary path taken by lower mass stars. A study published in 2021 argued for the latter interpretation, which would make this the most luminous star of its kind ever found. The distinction matters. If it is a true supergiant, it will explode one day. If it is an asymptotic giant branch star, it will shed its outer layers more gently, leaving behind a white dwarf instead. Either way, its current state is extreme. Its atmosphere shows molecular water layers and maser emissions, which are naturally amplified beams of microwave radiation produced by excited molecules in the star's extended atmosphere. This star's luminosity is estimated at roughly 195,000 times that of our star. Its mass is about 12 times the mass of our star. It is losing material through powerful stellar winds, bleeding gas and dust into the surrounding space. The mass it is currently shedding contributes to a thick envelope of gas and dust surrounding the star. This envelope is so thick that it blocks most visible light from reaching us. Astronomers study it primarily through infrared and radio wavelengths, which can penetrate the dust. Even so, many of its properties remain uncertain: the distance, the mass, the true nature of the object. All of these carry significant error bars. What is certain is the scale. This is one of the largest pulsating objects ever observed, a star that changes its own width by a distance greater than the orbit of Mars around our star, every single cycle. And it does this repeatedly, cycle after cycle, as it slowly dies. The pulsation is violent, but there is something even more destructive happening in stars like this. Something that strips away their outer layers and throws material into space at incredible speeds. We see the star pulsing, growing, shrinking, dying in slow motion, and there is something even more destructive happening alongside the pulsation. Something that strips away the outer layers and throws material into space at speeds we can barely comprehend. The next chapter is about stellar winds, and what they do to the biggest stars is terrifying. There is a point where a star begins to destroy itself. It does not happen all at once. It happens slowly, relentlessly. Layer by layer, the outer atmosphere of a massive star is torn away and flung into space. Over thousands or millions of years, the star loses a significant fraction of its total mass through this process. By the time it finally collapses, the star may weigh far less than it did when it was born. This process is called stellar wind, and in the biggest red supergiants, it reaches levels that can only be described as catastrophic. Every star has some kind of stellar wind. Our star has one. It is called the solar wind, a stream of charged particles flowing outward from the surface at roughly 1,000,000 miles per hour. But the solar wind is gentle. It carries away only a tiny fraction of the star's mass each year. At the current rate, our star will lose less than 1/10 of its mass over its entire 10 billion year lifetime through wind alone. Red supergiants are different. The stellar winds from these dying giants are thousands to millions of times stronger than what our star produces. A red supergiant can lose the equivalent of one Earth mass every few weeks. Entire worlds worth of gas, ripped from the surface and hurled outward. Some of the most extreme examples shed material at rates equivalent to an entire Earth mass every few days. Over thousands of years, that adds up to entire planets' worth of gas and dust hurled into the surrounding space. The mechanism behind this extreme mass loss is still being studied. Scientists believe it involves a combination of factors. Radiation pressure plays a major role. The luminosity of a red supergiant is so enormous that the light itself pushes on the atoms and dust grains in the outer atmosphere, accelerating them outward. Pulsations contribute too. As the star's outer layers expand during each pulse cycle, some of the material reaches escape velocity and never falls back down, and convection adds another layer of violence. The massive rising and sinking currents on the star's surface can launch clumps of material outward like eruptions. The result is a star that is literally tearing itself apart from the outside in. The ejected material does not simply vanish, it forms enormous shells and clouds around the star. These circumstellar envelopes, as scientists call them, can stretch for light years in every direction. They contain dust, water molecules, carbon monoxide, silicon compounds, and many other molecules. In some cases, the envelopes are so thick that they completely obscure the star itself, hiding it from view at visible wavelengths. You can only see the star through infrared or radio telescopes that can peer through the dust. This mass loss has profound consequences for the star's evolution. A star that was born with 30 times the mass of our star might lose half of that mass before it finally dies. The amount of mass remaining in the core at the moment of collapse determines whether the remnant is a neutron star or a black hole. So the stellar wind does not just shape the star's appearance, it shapes its destiny. It determines the type of explosion, the type of remnant, and the amount of heavy elements scattered into the galaxy. And here is something that should give you pause. The stellar wind from a single red supergiant over its entire lifetime can contribute more material to the interstellar medium than the supernova explosion itself. The slow, steady stripping of the outer layers delivers a continuous supply of elements to the galaxy for thousands of years before the final detonation. The next star on our list is one of the most dramatic examples of extreme mass loss anywhere in the galaxy. It sits about 5,300 light-years away, wrapped in a complex, asymmetric shell of ejected material so thick that it was discovered not by its visible light, but by its infrared glow. In 1965, 3 astronomers in California pointed an infrared detector at the sky and found something that should not have been there. The constellation Cygnus, the swan, is one of the most recognizable shapes in the northern sky. It sits along the band of the Milky Way, and its stars are familiar to anyone who has spent time under a dark sky. But buried deep within Cygnus, invisible to the naked eye, and hidden behind thick curtains of interstellar dust, something enormous was glowing. It was so faint at visible wavelengths that no optical telescope had ever noticed it before. But in the infrared, it was blazing. The 3 discoverers, whose initials gave the star its name, had found one of the most extreme objects in our galaxy. This red hypergiant sits approximately 5,300 light-years from Earth. Its radius is estimated at roughly 1,350 times that of our star, based on the most recent and reliable measurements using radio interferometry. If it replaced our star, its surface would extend past the orbit of Jupiter. It shines with roughly 200,000 times the luminosity of our star when you account for all wavelengths. Its surface temperature hovers around 6,000 degrees Fahrenheit, cooler than our star, and deep in the red part of the spectrum. Most of its energy radiates in the infrared, which is why it went undetected for so long. But size and brightness are only part of the story. But the most striking feature of this star is its mass loss. It has one of the highest mass loss rates of any star ever measured in our entire galaxy. It is shedding material at a rate that scientists estimate at roughly 4 to 5 ten-thousandths of our star's entire mass every single year. To put that in perspective, that is roughly the mass of Jupiter being thrown into space every few thousand years. The material forms a complex, asymmetric envelope around the star, a bean-shaped cloud of gas and dust that has been imaged by the Hubble Space Telescope. Inside this cloud, astronomers have detected an astonishing variety of molecules: water vapor, silicon monoxide, carbon monoxide, hydrogen cyanide, sulfur compounds, ammonia. The circumstellar envelope is like a chemistry laboratory with molecules forming in the cooling gas as it flows away from the hot stellar surface. The star is also a source of natural maser emission. Certain molecules in the envelope become excited by the star's radiation and emit tightly focused beams of microwave light. These masers have been used to precisely measure the star's distance and motion through techniques called very long baseline interferometry, providing some of the most accurate data we have for any star of this extreme type in the galaxy. This star lives on the outskirts of one of the largest stellar associations in the galaxy, a massive group of hot, young stars that spans an enormous region of space. It is believed to have started its life as a star, roughly 25 times the mass of our star, and to be about 8 million years old. 8 million years old. That is the total lifespan so far for a star of this mass and luminosity. Our star is 4.5 billion years old and still in its prime. This giant burned through its fuel in a tiny fraction of that time, and now it sits on the edge of death, wrapped in a shroud of its own discarded material. The next stop brings us to one of the most extreme stellar neighborhoods in the Milky Way, a massive star cluster 12,000 light-years away, where dozens of rare, evolved stars orbit together. And among them is a red supergiant, surrounded by something no one expected to find. 12,000 light-years from Earth, there is a star cluster that reads like a catalogue of extremes. This cluster was discovered in 1961 during an infrared survey. For decades, it remained largely unstudied because the thick dust between it and Earth blocked most of the visible light. Only when astronomers began observing in infrared and radio wavelengths did the true nature of this cluster emerge. It is believed to be the most massive young star cluster in our entire galaxy. Packed inside a relatively small volume of space are 6 yellow hypergiants, 4 red supergiants, 24 Wolf-Rayet stars, a luminous blue variable, and a magnetar, a type of neutron star with an incredibly powerful magnetic field. This is an extraordinary collection of rare, extreme objects, all in one place. Among the red supergiants in this cluster, one stands out. It is one of the largest and most luminous red supergiants known anywhere. Its estimated radius ranges from 1,530 to 1,580 times that of our star, based on infrared brightness measurements and assumed temperatures. If you dropped it into the center of our solar system, it would swallow every planet out to Jupiter and reach significantly beyond. Its luminosity is estimated between 320,000 and 380,000 times that of our star. Those are extraordinary numbers, placing it among the most energetic, cool stars in the galaxy. But the most remarkable discovery came in 2013. Astronomers using the European Southern Observatory's Survey telescope found that this star is surrounded by a glowing cloud of ionized hydrogen. This is the first time an ionized nebula had been observed around a red supergiant through its optical emission lines. The nebula stretches over 1 parsec, roughly 3.3 light-years, from the star itself. That finding was puzzling. Red supergiants are too cool to ionize hydrogen on their own. The ultraviolet radiation needed to strip electrons from hydrogen atoms simply is not present at the surface temperatures these stars reach. So, where was the ionization coming from? The answer lies in the environment. This star lives inside a cluster filled with dozens of extremely hot blue stars and Wolf-Rayet stars. These neighbors pump out intense ultraviolet radiation. Scientists believe this external radiation is what ionizes the gas around the red supergiant. The ejected material from the dying giant drifts outward and is then lit up by the fierce radiation of its neighbors. The result is eerie. A massive, cool, red star sitting inside a glowing cocoon of ionized gas. A dying giant being illuminated by the very stars it was born alongside. The star has also been observed to change its spectral type over time, shifting its temperature without changing its overall luminosity. This suggests that the outer layers are in a state of upheaval, rearranging themselves as the star slowly loses mass and evolves. Some scientists believe this star may eventually evolve into a hotter supergiant before its core collapses. The mass loss we are witnessing right now could be the process that strips away the cool outer envelope, exposing the hotter layers beneath. The cluster itself is only about 4 to 5 million years old. That is young. These stars were born in a single burst of formation, meaning they all share similar ages and compositions. Studying them together gives astronomers a powerful way to test models of how massive stars live and die. But we are not done climbing. The next star on our journey lives in the southern sky, roughly 3,800 light-years away. It is wrapped in one of the most violent and complex nebulae ever observed around any star, and its story will push us closer to the very limits of what a star can be. 3,800 light-years from Earth, in the direction of the constellation Canis Major, there is a star that has fascinated and frustrated astronomers for over a century. It was first catalogued in the late 1800s. Even then, observers noted its deep red color and unusual brightness. Over the following decades, as telescopes improved, the true scale of this object began to emerge, and the numbers were difficult to accept. It was first catalogued in the late 1800s and has been puzzling astronomers ever since. This is one of the most extreme red supergiants, or hypergiants, ever studied in the Milky Way. Its estimated radius, based on the most recent and careful measurements, is roughly 1,420 times that of our star. Some older estimates placed it even higher, but modern techniques have brought the number down to a range that is still staggering. If this star sat where ours does, its surface would stretch past the orbit of Jupiter and approach the orbit of Saturn. Its luminosity is estimated at roughly 270,000 times that of our star. Its mass at birth was likely between 25 and 32 times the mass of ours. And its surface temperature hovers around 6,000 degrees Fahrenheit, cool enough to glow a deep, dark red. It is losing mass at a ferocious rate, shedding its outer layers into the void through powerful stellar winds. The material it expels does not simply drift away quietly. What sets this star apart from the others we have visited is the carnage surrounding it. This star is surrounded by one of the most complex and violent circumstellar environments ever observed around any individual star. Hubble Space Telescope images reveal a chaotic collection of arcs, knots, filaments, and loops of ejected material extending far from the surface. These features are not symmetrical. They are messy, asymmetric, and wildly irregular, suggesting that the mass loss from this star is anything but smooth. Some of the knots of ejected material are massive. Individual clumps in the nebula have been estimated to contain more mass than Jupiter. These are not gentle wisps of gas. They are dense, heavy chunks of matter, blasted away from the star's surface during violent episodes of eruption. Scientists have identified at least 24 discrete arcs and features in the surrounding nebula, each one likely representing a separate mass ejection event. The mass loss rate from this star is extreme. Estimates suggest it sheds roughly the equivalent of 30 Earth masses per year. Over thousands of years, this star has expelled an enormous amount of material, building up the complex nebula that now envelops it. Maser emissions from the circumstellar envelope have been used to precisely measure the distance and motion of the star. These observations confirm its membership in a stellar group and provide some of the most reliable data for any object of this type. The evolutionary state of this star is advanced. Its core has already burned through hydrogen and helium and is likely fusing heavier elements. The remaining fuel will not last long. Scientists expect this star to end in a supernova, and the remnant will almost certainly be a black hole. In 2025, new research suggested this star might actually be in a second red supergiant phase, meaning it may have already evolved to a hotter blue state and then returned to the red supergiant stage. If confirmed, this would represent one of the most extreme evolutionary loops a massive star can undergo. In 2025, new research suggested this star might actually be in a second red supergiant phase, meaning it may have already evolved to a hotter blue state and then returned to the red supergiant stage. If confirmed, this would represent one of the most extreme evolutionary loops a massive star can undergo. The nebula around this star tells a story that goes far beyond a single object. The cloud of gas surrounding the red monster of Canis Major is one of the most studied objects in modern astrophysics, and what scientists found inside it forced a rethinking of how massive stars die. Before this star was studied in detail, the standard model of red supergiant mass loss was relatively simple. The star pulsates. The outer layers expand. Radiation pressure and convection drive a steady wind outward. Material accumulates in a roughly spherical shell around the star. Clean, symmetrical, predictable. The reality turned out to be nothing like that. High-resolution images from the Hubble Space Telescope, combined with ground-based observations, revealed a nebula that is wildly asymmetric. The ejected material does not form anything close to a smooth shell. Instead, it creates a complex, chaotic, three-dimensional structure with arcs extending in multiple directions, dense knots scattered throughout, and filaments connecting different regions like a web. Scientists have identified features in this nebula that suggest the mass loss happened in distinct, violent episodes rather than a continuous wind. Each arc and clump appears to correspond to a separate eruption event, with different ages and velocities. By tracing the motions of these features backward in time, astronomers have reconstructed a rough timeline of the star's eruptive history over the past few thousand years. The picture that emerges is startling and overturned decades of assumptions. This star has been experiencing periodic, catastrophic eruptions, blasting enormous quantities of material into space at irregular intervals. Between these eruptions, the mass loss is still significant through steady stellar winds, but the bursts are what create the largest and most dramatic features in the nebula. This discovery had important implications for the broader study of massive star evolution. If stars like this one lose mass in violent, episodic bursts rather than smooth, continuous winds, then the final mass of the star at the moment of core collapse is much harder to predict. And the final mass is what determines the type of supernova and the nature of the remnant. Some of the knots in the nebula are so dense and massive that they have their own gravitational significance. They will not simply dissipate into the interstellar medium. They will persist as distinct structures for thousands or even millions of years, slowly mixing with the surrounding gas and contributing their heavy elements to the raw material for future stars and planets. Scientists believe we may be witnessing the final stages of this star's pre-supernova evolution, a period of increasingly violent mass ejection as the core contracts and heats up. The chemical composition of the nebula is rich. Oxygen, silicon, sulfur, and other heavy elements are present in significant quantities. These are elements that were forged inside the star's core and then expelled during the eruptions. When this star finally explodes, even more heavy elements will be added to the mix, and the combined contribution of the wind material and the supernova debris will seed a vast region of space with the ingredients for new worlds. This is stellar recycling at its most dramatic. The star takes hydrogen, converts it into dozens of heavier elements through nuclear fusion, and then sprays those elements across light years of space. Everything it produces becomes raw material for the next generation. The nebula around this star will persist long after the star itself is gone. It will expand, cool, and eventually merge with the surrounding interstellar medium. Millions of years from now, some of that material may collapse into a new star, carrying with it the atoms that were forged in the heart of this dying giant. But our journey is not over. The stars are still getting bigger, and the next one takes us somewhere we have never been before on this trip, outside the Milky Way, to a star in another galaxy entirely. 160,000 light-years from Earth, in a small companion galaxy orbiting our own, a star is dying inside an egg. The galaxy is the Large Magellanic Cloud, a satellite of the Milky Way visible from the southern hemisphere as a faint, glowing smudge in the night sky. It contains billions of stars, Most of them are unremarkable, but one of them is extraordinary. This star is a red supergiant with an estimated radius of roughly 1,540 times that of our star. That places it among the largest stars ever measured. Its luminosity is approximately 282,000 times that of our star. It was born with roughly 25 times the mass of ours, and it is losing mass at a furious rate. What makes this star historic is something that happened in 2024. Using the Very Large Telescope Interferometer in Chile, astronomers achieved something that had never been done before. They directly imaged a star outside the Milky Way in close-up detail. For the first time, we could see the actual shape and structure of an extragalactic star's immediate surroundings, not just a dot of light, but resolved features around the object itself. What they found was striking. The star is surrounded by a torus-shaped cloud of dust, a thick, ring-like structure that wraps around the star's equator. When viewed from our angle, the torus appears as an elongated, egg-shaped cocoon of warm dust enclosing the star. This dusty envelope absorbs a significant portion of the star's radiation and re-emits it in the infrared. The shape of the torus matters. Earlier estimates of this star's size and luminosity had assumed the dust shell was spherical. If the dust is distributed evenly in a sphere, you can calculate how much light it absorbs and correct for it. But the torus shape means the light escapes preferentially through the poles of the ring, rather than being absorbed equally in all directions. Previous calculations had overestimated the luminosity because they did not account for this geometry. The corrected luminosity, published in 2007, brought the star's numbers more in line with the largest red supergiants in our own galaxy. It is still massive, still extreme, but the egg-shaped dust cloud changed how we interpreted it. The star has also undergone significant changes in recent years. Photometric monitoring over 3 decades has shown that its brightness variability shifted from regular, semi-periodic pulsation to irregular and chaotic behavior around 2014. This transition suggests something is changing inside the star. It may be entering a new phase of its evolution. There is also growing evidence that this star is not alone. Since 2016, its spectrum has shown features consistent with a hot companion star, possibly a B-type star that is accreting material from the supergiant. If confirmed, this would make the system a symbiotic binary, with the companion feeding off the dying giant's expelled atmosphere. This system, if it is indeed a binary, adds another layer of complexity to an already extreme object. The fact that this star lives in another galaxy gives astronomers a unique advantage. The distance to the Large Magellanic Cloud is well established, which means the uncertainty in the star's luminosity is much smaller than for stars within our own galaxy, where distance measurements are harder. This star is roughly 1,540 times wider than ours, enormous by any standard. A dying colossus in a neighboring galaxy, wrapped in a dusty cocoon, possibly being cannibalized by a companion. And it was the first star beyond the Milky Way to be seen in such intimate detail. But it is still not the largest. The next star on our journey was once considered the biggest of them all. It held that title for years, and then the measurement changed. For years, it was the answer to the question, what is the biggest star in the universe? It appeared in documentaries. It was featured in YouTube videos. It showed up in size comparison charts that went viral online, showing a tiny dot labeled "Our Star" next to an impossibly large sphere. The number that appeared in those graphics was 1,708 times the radius of our star, a figure so large it seemed unreal. And it was wrong. This star sits in the constellation Scutum, roughly 5,500 light-years from Earth. It is a red supergiant, classified as a pulsating variable. It was first catalogued in the early 1900s, but it became famous much later, when a study published in 2012 calculated a radius that placed it as the largest known star. The measurement was based on a specific distance estimate and a calculated luminosity. At the time, the best available data suggested the star was farther away than later studies would show. And when a star appears to be farther, its luminosity must be higher to account for the same observed brightness. Higher luminosity, combined with the measured temperature, yields a larger radius. Then the data was revised. Newer observations, including significantly more precise distance measurements from modern surveys and updated atmospheric models, brought the numbers down significantly. The revised radius fell into a range of roughly 755 to 909 times the width of our star. That is still an enormous, impressive number. It is still a red supergiant of impressive scale, but it was less than half the previous estimate. Overnight, the star went from being the unquestioned largest known star to being roughly comparable in size to Betelgeuse or Antares. The title of largest star shifted to other candidates. The internet comparisons became outdated, and a crucial lesson became clear, one that applies to every star on this journey. Measuring the size of a distant, bloated, pulsating, dust-shrouded star is extraordinarily difficult. Small changes in the assumed distance can cause enormous changes in the calculated radius. And for the most extreme stars, the uncertainty can be massive. This star is still a genuinely fascinating object in its own right. It is a massive, evolved, red supergiant in the late stages of its life. It pulses with a period of roughly 740 days. Its brightness varies significantly over that cycle. It is losing mass through stellar winds. It is surrounded by a cloud of ejected material, and it will eventually die in a supernova. Scientists continue to study this star, refining its properties with each new observation. Its exact size may shift again as better data arrives, but its fall from the top of the size chart illustrates a fundamental challenge in this field. The title of largest star is not permanent. It depends on the quality of the latest measurements. A single new study, a single revised distance, can reshuffle the entire list. This has happened before, and it will happen again. As better telescopes come online and better measurement techniques are developed, the numbers will continue to change. Some stars currently considered modest may turn out to be much larger than we thought. Some current giants may shrink when remeasured. This is important because every size record in astronomy is provisional. When you hear that a star holds the title of largest, remember that the title comes with fine print. The number depends on the distance, the temperature, the model, and the moment in time when the measurement was taken. The question is not just which star is biggest right now. The question is whether our measurements will ever be precise enough to give a permanent, definitive answer. And that is exactly the problem the next chapter addresses. We have been climbing a ladder of size throughout this journey, each star bigger than the last, each number more extreme. But behind every one of those numbers is a chain of measurements, assumptions, and uncertainties that most people never see. The truth is, the largest stars in the universe are also the hardest to measure accurately, and the reasons go deeper than you might expect. The challenge begins with the most fundamental measurement in astronomy: distance. Every calculation of a star's physical size depends on knowing how far away it is. If the distance is wrong by 20%, the radius estimate can be wrong by the same amount or more. For nearby stars, parallax measurements from spacecraft like Gaia can pin down distance with great precision. But the biggest red supergiants tend to be thousands of light years away, where parallax angles become tiny and the measurements carry large error bars. Even a 10% error in distance can translate to a 20% error in the final radius estimate. That alone is enough to move a star up or down several places in the rankings. Then there is the problem of the star itself. Red supergiants are not clean, well-defined objects. They do not have sharp edges. Their outer atmospheres are so diffuse that they fade gradually into the surrounding space. Where the star ends and the circumstellar material begins is a judgment call. Different wavelengths of light reveal different apparent sizes. If you observe in the infrared, the star looks larger because you are picking up emission from warm dust in the surrounding envelope. If you observe invisible light, the star looks smaller because you are seeing closer to the actual photosphere. Adding to the confusion, many of the largest stars are surrounded by thick shells of dust and molecular gas that they have expelled through their stellar winds. This material absorbs and re-emits radiation, which can fool measurements of both brightness and apparent size. Correcting for this absorption requires assumptions about the shape, density, and composition of the dust. Different assumptions lead to different answers. Then there is pulsation. The biggest stars change size. Literally, over cycles of hundreds or thousands of days, their radii can swing by a significant percentage. A star measured at maximum expansion will appear larger than the same star measured months later at minimum. If two different teams measure the same star at different points in its cycle, they will get different radii. Both measurements can be correct, yet the numbers will disagree. Temperature adds another layer of uncertainty. To convert from luminosity to radius, you need to know the effective temperature of the star's surface. Temperature measurements for cool red supergiants are notoriously difficult because their spectra are crowded with molecular absorption bands. Small changes in the assumed temperature can shift the calculated radius by hundreds of times the width of our star. And finally, there is the question of what radius even means for these objects. In a normal star, the photosphere is a well-defined boundary. In a red supergiant, the concept breaks down. The atmosphere extends outward in layers of decreasing density, each layer contributing its own emission and absorption. Different definitions of surface give different sizes. All of this means that the rankings of the largest stars should be treated with caution. The numbers are real, the science is solid, but the error bars are wide, and the list can change with every new observation. This is the messy, uncertain, constantly evolving reality behind every size estimate on our journey. The science is real, the methods are sound, but the answers always come with question marks attached. With that understanding, we are ready to meet the current champion, the star that, as of our best measurements today, holds the title of the largest known star in the universe. 20,000 light-years from Earth, buried deep inside the Milky Way, there is a star that defies what physics says should be possible. It lives in a dense, heavily obscured star cluster located near the constellation Scutum. The cluster is hard to study because it lies along a line of sight that passes through thick clouds of interstellar dust. Most of the stars in the cluster are invisible at optical wavelengths. Only infrared observations can penetrate the veil. Among the dozens of massive stars in this cluster, one stands out. Its estimated radius is roughly 2,150 times that of our star. 2,150. That is the current best estimate based on luminosity calculations and temperature measurements published in a 2012 study. Let that number sink in for a moment. If you placed this star at the center of our solar system, its surface would extend far past the orbit of Saturn. It would reach approximately to the orbit of Uranus. Mercury, Venus, Earth, Mars, Jupiter, and Saturn would all be inside this single star. The volume it occupies is roughly 10 billion times greater than the volume of our star. Its luminosity is estimated at roughly 440,000 times that of our star. That places it among the most luminous cool stars in the entire Milky Way. Its surface temperature is around 5,800 degrees Fahrenheit, cool enough to glow deep red, with most of its energy radiating in the infrared. It is classified as a red supergiant, spectral type M6, one of the coolest supergiants known. The mass it was born with is uncertain, but estimates place it somewhere between 12 and 40 times the mass of our star. It is losing material through stellar winds, and its current mass may be significantly lower than its birth mass. The mass loss rate is not precisely known, but it is believed to be substantial. Like all red supergiants of this scale, it is bleeding material into the surrounding space, contributing heavy elements to the interstellar medium. Finding this star was not easy. The cluster it belongs to is one of the most heavily reddened star clusters known, meaning that the interstellar dust between us and the cluster absorbs enormous amounts of visible light. Without infrared telescopes, this star and its entire cluster would be completely invisible. The star was identified as a member of the cluster through its infrared colors and brightness. Its extreme luminosity and cool temperature place it in the upper right corner of the Hertzsprung-Russell diagram, the region occupied by the most extreme red supergiants and hypergiants. But here is the problem that haunts this measurement. Everything about this star depends on the assumed distance to the cluster. If the cluster is closer than currently estimated, the star is less luminous and therefore smaller. If it is farther, the star could be even larger. Distance measurements for objects 20,000 light-years away, behind thick dust, in the crowded inner regions of the galaxy, carry significant uncertainty. Scientists have used multiple methods to estimate the distance, including radial velocities and comparisons with other clusters. The current consensus places the cluster at roughly 6 kiloparsecs, or about 20,000 light-years. But this number could shift as better data becomes available. And the distance is not the only uncertainty. The temperature, the extinction from dust, and the exact luminosity all carry their own error bars. Each one affects the final radius number. Even with that caveat, the scale is extraordinary. No other star currently measured comes close to the estimated radius of this object. It sits alone at the top of every size comparison chart. And the deeper question is not whether the measurement is perfect. The deeper question is whether a star this large should exist at all. Let us try to picture it. Take the largest known star and place it where our star sits right now. Drop it into the center of our solar system and see what happens. The first thing you would notice is that everything close is gone. Mercury, Venus, Earth, Mars. All of them would be deep inside the star, not just near the surface. Deep, hundreds of millions of miles below the outer edge. At Earth's current distance from the center, about 93 million miles, we would be so far inside this star that the surface would still be over 1 billion miles above us. Jupiter would be inside the star too. At roughly 484 million miles from the center, Jupiter's orbit falls well within the radius of this giant. It would be engulfed. Its moons, its rings of faint dust, its massive atmosphere of hydrogen and helium, all of it consumed. Saturn, sitting at roughly 890 million miles from the center, might survive, barely. Depending on the exact radius estimate and the phase of the star's pulsation, Saturn could be just outside the surface, orbiting through the thin, extended outer atmosphere. Or it could be swallowed completely. Everything, from Mercury to Saturn, the entire inner and middle solar system, replaced by the interior of a single star. Uranus and Neptune would remain outside, orbiting in the cold, dark space beyond the star's edge. But everything between here and there, every world, every moon, every asteroid, every comet in the inner and middle solar system would cease to exist as independent objects. They would simply be swallowed. Now, what would conditions be like inside this object? At the star's surface, the temperature is roughly 5,800 degrees Fahrenheit. That is actually cooler than the surface of our star, which sits around 10,000 degrees. But the density at the surface of this giant is almost nothing. The gas in the outer layers of a red supergiant this large is thinner than the best laboratory vacuum on Earth. You could theoretically fly a spacecraft through the outer regions of this star and encounter fewer particles per cubic inch than you would in an empty sealed container on our planet. That is one of the strangest things about these stars. They are enormous, but they are mostly empty space. The mass is concentrated in the core, which is relatively tiny compared to the overall size. The outer layers are just a thin, hot fog stretching across 1 billion miles. The gravity at the surface of this star would be almost undetectable compared to the surface gravity of our star. Because the mass is spread so thin, the gravitational pull at the edge would be a tiny fraction of what we experience on Earth. This weak surface gravity is part of why the star can grow so large in the first place. There is simply not enough gravitational force at the edge to hold the material down. The radiation pressure from the interior pushes it outward, and gravity cannot push it back. If you were somehow standing at the surface of this star, looking inward, you would see nothing. The gas is too diffuse to block your line of sight. You would be standing in a faintly glowing red fog, with no visible ground beneath you and no clear sky above. Just a gradually brightening haze as you look toward the distant core, 1,000 times the width of our star away. This is the scale of the largest known star, a volume that could contain 10 billion copies of our star. A sphere so large that light itself, traveling at 186,000 miles per second, takes over 8 hours to cross from one side to the other. And according to current theory, it should not exist. There is a limit to how large a star can grow. It is called the Hayashi limit, and it represents a boundary in the physics of stellar structure. The idea is straightforward. As a star expands and cools, its outer layers become convective, meaning the energy is transported outward by rising and sinking currents of gas rather than by radiation. There is a minimum temperature at which a star of a given luminosity can maintain this convective structure. If it cools below that temperature, the physics says it should become unstable and either collapse or shed its outer layers until it reaches a stable state. For the most luminous red supergiants, this boundary sits at a radius of roughly 1,500 times that of our star. Stars can approach this limit, but the models say they should not significantly exceed it. The Hayashi limit is a theoretical wall. The largest known star appears to be on the other side of that wall. At 2,150 times the radius of our star, this object significantly exceeds the Hayashi limit. Its size places it in a region of the Hertzsprung-Russell diagram, where stellar models say stable stars should not exist. This has led to significant scientific debate about what this star actually is, how it got there, and whether our models need to be revised. There are several possible explanations that scientists have proposed, and none of them are simple. The first possibility is that the measurement is wrong. If the distance to the star's cluster has been overestimated, or if the temperature has been miscalculated, the true radius could be smaller. Bringing it back below or near the Hayashi limit would resolve the contradiction. Given the difficulty of measuring stars this far away, behind this much dust, this remains a real possibility. The second possibility is that the star is in a temporary, unstable phase. Perhaps it has recently experienced a dramatic expansion due to a shell-burning episode or a merger event, and it has temporarily inflated beyond the theoretical limit. If so, it would be expected to contract or shed material until it returns to a stable configuration. We might be catching it in a brief, extreme moment. The third possibility is the most exciting. Our models might be incomplete. The Hayashi limit was derived using certain assumptions about how convection works in the outer layers of massive stars. If those assumptions are wrong, if convection in real stars behaves differently than in models, then the limit itself might be wrong. Discovering a star that exceeds the limit could be evidence that our understanding of stellar physics needs to be updated. Several researchers have explored this third option. Some have proposed that extreme mass loss, rotation, or magnetic fields might alter the conditions in the outer layers enough to allow the star to expand beyond the theoretical boundary. Others have suggested that interactions with companion stars or unusual chemical compositions could play a role. The truth is, we do not know which explanation is correct. This star sits at the frontier of our understanding, in a place where theory and observation have not yet been fully reconciled. And that is exactly what makes it so important. Stars like this one are not just curiosities. They are tests. Each one that exceeds our expectations forces us to examine our models more carefully, look for errors in our calculations, and consider whether the universe is doing something we have not accounted for. The largest known star is a challenge to physics itself, a glowing, dying, impossibly large challenge, sitting 20,000 light-years away in a dusty corner of the Milky Way, daring us to explain it. And while we grapple with that challenge, the star itself does not care. It is busy doing something far more important. Deep inside every red supergiant, something extraordinary is happening. The core of the star is a forge, a furnace operating at hundreds of millions of degrees, crushing atoms together under pressures that would flatten anything we know. And inside that forge, the universe is building the elements that make everything possible. We have talked about fusion earlier in this journey. Hydrogen becomes helium, helium becomes carbon, carbon becomes neon, then oxygen, then silicon, then iron. But we have not talked about what this actually means for the universe at large. Consider this, because it is one of the most profound facts in all of science. Almost every atom in your body that is heavier than hydrogen was created inside a star. The carbon in your muscles, the oxygen you breathe, the iron in your blood, the phosphorus in your DNA, the calcium in your teeth. All of it was manufactured inside the core of a massive star, transported to the surface through convection and dredge-up processes, and then either expelled through stellar winds or released in the final supernova explosion. The red supergiants we have been visiting are the primary factories for this process. During their bloated, dying phase, they are actively shedding heavy elements into the galaxy through their intense mass loss. Carbon, oxygen, and silicon-rich dust grains form in the cooling outflows around these stars, condensing from the hot gas like snowflakes forming in a winter storm. These dust grains drift into interstellar space, mix with hydrogen clouds, and eventually become part of new collapsing regions where future stars and planets will form. When the core finally reaches iron and collapses, the supernova itself does something even more remarkable. The extreme temperatures and neutron densities during the explosion trigger a process called rapid neutron capture. Free neutrons slam into atomic nuclei faster than those nuclei can decay. This builds up heavier and heavier elements in fractions of a second: gold, platinum, uranium, thorium. Every element heavier than iron on the periodic table was created through this process, or one similar to it, during the death of a massive star. The gold in a wedding ring was forged in the final seconds of a supernova. The iodine in your thyroid was produced the same way. The zinc that helps your immune system function was born in a stellar explosion billions of years ago. That is confirmed science, supported by spectroscopic observations of supernova remnants and by nuclear physics calculations. The red supergiants on our journey are all at various stages of this process. Some are still forging carbon and oxygen. Others have moved on to silicon. At least one of them, perhaps the largest, may be approaching the iron wall, the point of no return where the core can no longer produce energy through fusion and must collapse. When that collapse happens, the explosion will scatter the star's carefully forged elements across dozens of light years. Over millions of years, that material will cool, drift, and mix with the surrounding gas. Some of it will be incorporated into new molecular clouds. Those clouds will collapse under their own gravity. New stars will ignite at their centers. Planets will form in orbits around them. And on some of those planets, under the right conditions, the heavy elements will arrange themselves into molecules, then cells, then organisms, then minds, capable of wondering where it all came from. That is the grand cycle of the cosmos. Stars forge elements, stars die. The elements become new stars and new worlds, and the process continues. Every red supergiant is a link in that chain. Every one of them is building the ingredients for whatever comes next. We are, in a very literal sense, the recycled remains of ancient stellar furnaces. The story of the larger stars is really the story of where everything comes from. We have traveled from our own star to the largest known object in the sky. We have crossed the Milky Way and even reached into a neighboring galaxy. We have measured stars hundreds, thousands, and over 2,000 times the width of our star. But here is the question that every astronomer working in this field asks themselves. Is there something bigger? The honest answer is, almost certainly. We have only surveyed a fraction of the stars in our galaxy. The Milky Way contains roughly 200 to 400 billion stars. We have detailed measurements for a tiny percentage of those. The most extreme objects tend to be hidden behind thick curtains of interstellar dust, buried in crowded star-forming regions, or simply too far away for current telescopes to study in detail. The largest known star was not discovered because anyone went looking for the biggest star. It was found during a survey of a heavily obscured star cluster that most astronomers had barely studied. It showed up in the data almost by accident. There could be others like it, sitting in clusters we have not yet catalogued, in regions of the galaxy we have not yet surveyed. Infrared and radio telescopes have opened up vast new windows into the hidden regions of the Milky Way. The dust that blocks visible light is transparent at these longer wavelengths. Missions like the James Webb Space Telescope and future ground-based observatories will allow astronomers to probe deeper into the galaxy's obscured zones than ever before. It is entirely plausible that within the next decade, a new star will be measured with a radius exceeding 2,150 times that of our star. There is also the question of other galaxies. The imaging of the giant in the Large Magellanic Cloud in 2024 proved that we can now resolve individual massive stars in nearby galaxies. As this technique improves, astronomers will be able to measure the sizes of red supergiants in dozens of satellite galaxies and beyond. Different galaxies have different chemical compositions, different star formation histories, and different environments. It is possible that the conditions in some other galaxy allow stars to grow even larger than anything in the Milky Way. Then there are the unknowns. Theoretical models suggest that the size limit for red supergiants depends on factors like metallicity, rotation, mass loss rates, and binary interactions. These factors vary wildly across different environments. There may be extreme stars in exotic conditions, perhaps in low metallicity galaxies where stellar winds are weaker and stars can retain more of their mass, growing even larger before they die. What we know for certain is this: the universe has been building stars for over 13 billion years. It has had countless opportunities to create objects at the very edge of what physics allows. We have only been looking with the right tools for a few decades. The largest star we have found so far is almost certainly not the largest star that exists. Somewhere out there, behind a wall of dust, in a distant corner of the galaxy or in a neighboring galaxy we have barely glanced at, there may be a star that makes everything on our journey look small. We just have not found it yet, and that is perhaps the most extraordinary thing about this journey. We started with a star we see every day, the one that lights our world, and traveled all the way to a dying colossus 2,000 times wider than it. We watched stars that bleed carbon, stars that pulse like beating hearts, stars that rip themselves apart and scatter their remains across light years of space. Every one of those atoms, every heavy element forged in those stellar furnaces, is part of the chain that leads to us. We are made of dead stars. We are made of supernovae. We are the universe looking at itself and asking how large it can possibly get. The answer, it seems, is larger than we ever imagined, and we are still searching,